Imagine you're standing in front of a truly massive puzzle. Maybe you're trying to predict housing prices, but instead of just square footage and bedrooms, you have thousands of characteristics. The type of plumbing from 1957, the exact shade of blue in the bathroom tiles, maybe even the average daily squirrel sightings in the yard.
Right, or maybe you're predicting medical outcomes from vast health records with, thousands of genetic markers, lifestyle choices, environmental factors.
Exactly. You have more potential pieces of information than you could ever possibly know what to do with. How on earth do you make sense of it all? How do you get the best prediction without getting completely swamped?
It's like trying to find a needle in a haystack, isn't it? But the haystack isn't just enormous, it's filled with millions of tiny, almost identical strands of hay, and you suspect maybe only a handful are actually useful for finding that needle. The sheer volume can be overwhelming.
A truly massive haystack. So, okay, how do we even begin to tackle this? How do we find that needle without getting buried?
Well, that's where these specialized tools come in.
Right. And our mission today is to embark on a deep dive into this fascinating world of penalized regression methods. These are powerful tools designed specifically for this challenge. We'll kind of follow a journey, right? From understanding the problem itself to why the traditional methods fall short.
And then explore these really quite clever solutions like Lasso, Ridge, Elastic Net, and even Lava.
Exactly. And our primary guide for this exploration, offering some really cutting-edge insights, is a chapter from Applied Causal Inference, powered by ML and AI, by Victor Chernozhukov and his co-authors.
Yeah, it's a fantastic resource, really foundational work that cuts through a lot of the complexity here.
So, by the end of this deep dive, you should have a really clear understanding of what these high-dimensional settings actually mean, why the methods we usually reach for struggle so much, and how these advanced regression techniques offer, well, pretty clever solutions and real-world advantages for building solid prediction rules.
You'll definitely get a shortcut to being well-informed on this whole area. It's becoming so crucial in modern data analysis.
Okay, let's dive in then, starting with that fundamental challenge. What does high-dimensional actually mean in this context, in regression? Is it just about having, like, tons of data?
Fundamentally, no, it's more specific than that. It describes a situation where you have more potential predictor variables, we usually call those P, than you have actual observations or individual data points, which we call N.
So PN, more predictors than observations.
Exactly. It's not just about the absolute amount of raw data you have, it's that critical ratio between the two.
And why does this scenario, this PNN thing, why does it happen so often these days? Seems like it's everywhere.
Yeah, it really is. There are a couple of major reasons. First, modern data sets just come packed with a lot of features.
Okay.
Think about all the different characteristics describing countries if you're doing global wealth analysis, or the sheer volume of detailed individual health information in electronic medical records.
Or like product details and online sales data.
Exactly. Or every tiny product detail captured in demand analysis. We're just collecting way more granular data than ever before.
But it's not just the raw features we collect, is it?
Right.
I gather we also kind of contribute to this high dimensionality ourselves.
Precisely. That's the second major reason. We often create many technical regressors or constructed features from the raw data we already have.
How do we do that? What kind of things?
Well, this could involve using polynomials like, say, adding squared or cubic terms for experience when you're analyzing wages, or using things called splines, or even creating interaction terms between variables where you multiply different features together.
Oh, like seeing if education matters differently depending on experience level.
Exactly like that. Or you might just apply functions like logarithms to transform some of your existing variables.
Okay, and why go through all that trouble? Why construct these extra features?
Yeah.
What's the payoff?
Well, the main motivation is to build more flexible models, ones that can potentially give you much better predictions. These constructed features allow our models to capture more subtle, nonlinear patterns in the original data that a simple straight-line relationship just wouldn't see.
So you get a richer model.
You get a richer model, exactly. But what's neat is even though the model becomes richer, it usually remains linear in these newly constructed regressors and their parameters. So it still fits nicely within that familiar regression framework.
Okay, so we have all this data. Maybe we've even constructed more features, and now we're squarely in this high-dimensional world. Our immediate thought might be, okay, fine. Why not just throw it all into a classic ordinary least squares regression, OLS? But something tells me it's not quite that simple.
Oh, absolutely not. That's where things really start to bane down. The huge problem is acute overfitting.
Overfitting.
OLS just tends to overfit massively in these high-dimensional settings. What that means is it essentially memorizes the noise and the unique quirks of your specific data set. It finds patterns that are unique only to that data.
And don't generalize.
Exactly. They don't generalize to new, unseen data from the same population. So the model becomes overly complex. It boosts its in-sample fit, how well it predicts the data it was trained on.
Which looks great on paper.
Looks great initially, yeah. But it severely harms the out-of-sample prediction performance, which is, let's face it, what we truly care about for any real-world application.
Yeah, that's a huge issue. It sounds like throwing spaghetti at the wall and hoping it sticks, but then the spaghetti just molds to every tiny imperfection on the wall rather than showing you the actual flat surface underneath.
That's a great analogy. And the source even mentions an extreme case of this overfitting.
Oh, yeah.
It's quite dramatic, actually. When Paley, the number of predictors is greater than or equal to in the number of observations.
So as many predictors as data points, or even more.
Right. In that situation, OLS can literally fit the data perfectly. It can draw a line, or technically a hyperplane, that passes through every single data point.
Wow. Regardless of the true relationship.
Regardless of whether there's any true, meaningful relationship there at all, that's a clear, very dangerous sign that your model is just memorizing noise, not learning anything useful.
Okay, so if OLS simply overfits when facing too much data,
Yeah.
how do these newer methods, these penalized methods, prevent that? What's their core trick? I understand they start with a really key assumption called approximate sparsity. Can you sort of walk us through the intuition there?
Yeah, the intuition is actually pretty elegant and powerful. Remember that enormous pool of potential predictor variables we talked about? The thousands of housing characteristics or medical factors?
Right, the giant haystack.
Exactly. Approximate sparsity suggests that out of that vast collection, maybe only a small group of variables truly have large, important coefficients that significantly explain the outcome you care about. The rest, the vast majority, they might have some tiny effect, but their coefficients are very small or basically negligible. They're mostly noise or just not very relevant.
So it's like saying that out of 1,000 possible reasons why house prices vary, maybe only, say, 20 are really driving the differences, and the other 980 are just background chatter.
Precisely. Or think about sorting all your potential predictors by how important they are, maybe by the size of their true effect. Approximate sparsity means the first few are incredibly powerful, the next few are somewhat helpful, and then after that, the importance just dropped off really quickly. The vast majority become almost irrelevant.
Like an 80-20 rule, but maybe even more extreme sometimes.
Could be, yeah, like 955. This critical assumption is what allows these methods to effectively sort of prune the irrelevant variables and focus on the important ones, which is how they avoid that massive overfitting problem of OLS.
That makes perfect sense.
Okay.
So let's talk about the first big player in this game, Lasso. What exactly is Lasso, and how does it implement this idea of pruning or focusing?
So, Lasso, it stands for least absolute shrinkage and selection operator. It basically modifies the standard least squares problem we know from OLS. It takes the usual sum of squared prediction errors.
How well the model fits the data.
Right, that part. And then it adds a specific penalty term to it.
A penalty. A penalty for what exactly? What does that term look like?
The penalty is based on the sum of the absolute values of the regression coefficients. So you take each coefficient, ignore its sign, positive or negative, just take its size, and add them all up.
Okay, the absolute values.
Formally, we call that an L1 penalty. And crucially, this sum is multiplied by a penalty level, which is often denoted by the Greek letter lambda. Sometimes there are also penalty loadings involved, typically related to the variance of the predictors, but the core idea is that lambda times the sum of absolute coefficients.
And the goal then is?
The goal of Lasso is to find the coefficient values that minimize a combination of two things: how well the model fits the data, the usual sum of squared errors, and the size of this L1 penalty term. It's looking for the best trade-off between fit and model complexity, where complexity is measured by the magnitude of its coefficients.
Okay, so how does adding this specific L1 penalty actually help Lasso fight overfitting? And I think you mentioned it does something else interesting too, beyond just shrinking coefficients.
Absolutely. It does two key things. First, because that penalty level, lambda, is positive, Lasso forces the overall magnitude of the estimated coefficients to be smaller than they would be without the penalty. This is often called shrinkage bias or regularization bias.
It shrinks them towards zero.
Exactly, it pulls them towards zero. And this shrinkage directly guards against overfitting because it actively penalizes complexity. It stops the model from making tiny idiosyncratic improvements to the in-sample fit using large coefficients, improvements that likely won't generalize to new data.
Okay, that's the shrinkage part. What's the other thing?
The other thing is the really fascinating part, and it comes from the shape of that L1 penalty. Because it uses absolute values, the penalty function has a sharp kink right at zero. Unlike a squared penalty like RID uses, this kink means there's always a positive marginal cost for including any regressor in the model, even a tiny one.
A cost for just being non-zero at all. And what's the practical consequence of that kink at zero?
The result is pretty remarkable. Lasso effectively performs variable selection as part of the fitting process. If a variable's marginal predictive benefit, how much adding it improves the fit, doesn't exceed this sort of minimum cost threshold imposed by the kink,
That gets kicked out.
its coefficient is set exactly to zero. It's literally dropped from the model. It's like Lasso has a built-in editor function that automatically cuts out the variables that aren't pulling their weight enough to justify their complexity cost.
Wow. Okay, so it automatically throws out the less important stuff right there in the process. That sounds incredibly useful, especially with thousands of potential variables. The source even gives a simulation example of this, right?
It does, yeah. Example 3.1.1 describes a simulation where they set up a situation with, I think it was 300 observations and 1,000 potential variables.
Definitely high dimensional.
Oh, yeah. And the true coefficients in their simulation were designed to be approximately sparse, meaning only a few were really important. And Lasso did exactly what you'd hope. It successfully set most of the estimated coefficients to zero, effectively approximating that true sparse structure. It's a really neat demonstration of its variable selection power in action.
Okay, this raises a really important question, though, and it's something crucial for you listening to understand. Does Lasso always select the perfect set of variables? Does it guarantee finding only those variables with truly non-zero coefficients in the real world? Or is there maybe a nuance to its variable selection?
That's a key distinction, and the answer is no, it's not perfect in that sense. While Lasso is generally excellent for prediction, its variable selection isn't infallible when it comes to identifying the exact set of true underlying variables.
Why not? What can go wrong?
Well, a couple of things. It might exclude variables that have small but still genuinely non-zero true coefficients. If their effect is too small to overcome that penalty threshold, they get zeroed out.
Okay.
And maybe more importantly, it can really struggle sometimes when your predictor variables are highly correlated with each other. If you have a group of, say, 3 variables that are all important and all highly correlated, Lasso might just pick one of them somewhat arbitrarily and set the other 2 to 0, even though they're also truly relevant.
I see. So the big takeaway here is Lasso is a superstar for prediction, but you shouldn't necessarily take the exact set of variables it selects as the definitive list of true causal factors. It's more like a predictive scalpel, maybe not a microscope for uncovering root causes.
Exactly. That's a great way to put it. It's an incredibly powerful tool.
Right.
But always remember, its primary purpose is maximizing predictive accuracy, not necessarily perfect structural discovery or causal identification.
That's a crucial point. Now, for any of these methods, a critical piece is choosing the right tuning parameter, in Lasso's case, that penalty parameter, lambda. How do you actually pick the right value for lambda? Seems pretty important.
It is absolutely crucial, yes. The authors mention there's a theoretically valid choice, which involves using a formula based on things like the variance of the errors, the sample size, and maybe a desired confidence level. It gives you a starting point grounded in theory.
Okay, but is that what people usually do in practice?
Often, especially for building robust predictive models, a more widely used and generally preferred method is cross-validation.
Right, cross-validation. Can you just quickly remind us what that involves?
Sure. The basic idea is you repeatedly split your available data. You might split it into, say, 10 parts or folds. You then train the Lasso model on 9 of those parts for a specific value of lambda, and you test how well it predicts the 10th part, the part it hasn't seen.
The holdout set.
Exactly. And you rotate which part is held out, doing this 10 times. You repeat this whole process for many different possible values of lambda. Then you calculate the average prediction error across all those holdout sets for each lambda.
And you just pick the lambda that gives the lowest average error.
Precisely. You choose the lambda value that minimizes the average prediction error across all those validation splits. It's a very robust, data-driven way to find the lambda that offers the best trade-off between bias, underfitting, and variance, overfitting, for your specific data set.
Makes sense. Okay, so building on Lasso, the chapter then talks about something called post-Lasso. What is post-Lasso, and why would you add this extra step after running Lasso?
So post-Lasso is pretty much what it sounds like. First, you run Lasso, and it selects a set of variables, the ones that ended up with non-zero coefficients.
Right, the ones Lasso deemed important enough.
Exactly. Then post-Lasso takes only that selected set of variables and refits a standard ordinary least squares OLS model using just those predictors.
Ah, okay. So you use Lasso for the selection step, and then you run a simple OLS on just the chosen ones. Why do that? If Lasso already did the hard work of selection and estimation, what's the benefit of this second OLS step? What are we trying to, fix or undo?
It's all about undoing that shrinkage bias we talked about earlier with Lasso. Remember, Lasso, because of its penalty, shrinks all the non-zero coefficients it estimates towards zero.
Even the ones it keeps?
Even the ones it keeps, yes. They're all biased slightly downwards in magnitude. Post-Lasso essentially undoes this shrinkage bias for those selected coefficients. By running OLS just on the selected variables, it allows their magnitudes to be estimated without that L1 penalty's influence, potentially getting them closer to their true population values.
I see. So it can sometimes lead to more accurate coefficient estimates for the selected variables.
It can, yes. And this might, in some cases, lead to further marginal improvements in predictive performance compared to standard Lasso. It's particularly useful if you also care about interpreting the magnitudes of the coefficients that were selected.
That makes a lot of sense. You get the benefit of Lasso's powerful variable selection, and then you try to get a less biased estimate of the effects for those chosen variables. Now, is there a crucial practical note we should be aware of, especially when using cross-validation perhaps with post-Lasso? The authors seem to emphasize something here.
Yes, this is absolutely critical for anyone applying this in practice. If you're going to use post-Lasso, you have two main valid ways to handle the tuning parameter, lambda, from the initial Lasso step. You should either rely on that theoretically justified penalty parameter we mentioned earlier.
The formula-based one.
Right. Or, if you prefer to use cross-validation, you need to cross-validate the entire post-Lasso procedure together. That means for each potential lambda, you do the Lasso selection and the subsequent OLS refitting within each cross-validation fold before evaluating the prediction error.
Okay, so you evaluate the whole two-step process.
Exactly. What you should not do, and this is the key warning, is use cross-validation to pick the best lambda for Lasso alone, and then just take that single chosen lambda, run Lasso once on the full data to get the selected variables, and then run OLS on those selected variables.
Why is that bad? Seems intuitive.
It seems intuitive, but it can lead to surprisingly poor empirical performance. Essentially, the lambda chosen to optimize Lasso's prediction error might not be the lambda that selects the variable set that performs best after the OLS refitting step. You need to evaluate the performance of the combined procedure. It's about being consistent in your validation strategy.
Got it. That's a really important practical tip. So, stepping back a bit, what does this all mean for the quality of our predictions overall? We're using Lasso or post-Lasso, hoping to approximate the best linear prediction rule, the true underlying relationship in the population. How close do these methods actually get? Are there any theoretical guarantees?
Yes, there are some powerful theoretical guarantees, especially under that key assumption of approximate sparsity we discussed. The idea is that even though there might be potentially thousands of variables, if the true underlying relationship is driven by only a relatively small number of truly important variables, let's call this number S the effective dimension.
A number of needles in the haystack.
Kind of, yeah. If S isn't too large relative to your sample size N, and if the task of finding those as important variables among the picked candidates isn't overwhelmingly difficult, which is related to how distinct their signals are and how correlated they are, then the theory tells us that Lasso and post-Lasso can indeed get incredibly close to the ideal, best possible linear prediction rule.
So they can perform almost as well as if we knew the right variables from the start.
Almost. The guarantees often involve a term that looks something like S-log, max P NUN. If this term is small, then the prediction error of Lasso or post-Lasso will be close to the minimum achievable error.
Okay, and that log n factor that appears in there, what does that represent in simple terms? It seems like a penalty for having lots of variables.
That's exactly what it is. It captures the statistical price you pay for not knowing which of the potential regressors are the SIR's truly important ones up front. Lasso and post-Lasso have to search through the p variables to approximately find the s important ones. This search process, dealing with the potential for spurious correlations among the unimportant variables, comes with a small, unavoidable performance cost. It's the price of doing data mining, essentially, compared to an Oracle estimator that magically knows the best S variables from the very beginning.
Right, the Oracle doesn't have to search. So there's always maybe a slight trade-off for the intelligence and automation these algorithms provide, but the theory suggests it's often a very small price to pay, especially compared to the disaster of using OLS in these settings.
Precisely. The cost is typically logarithmic in p, which is usually much, much smaller than p itself, meaning the methods scale quite well.
And as always, the authors recommend a good practical rule of thumb.
Absolutely. Theory provides the foundation and tells us these methods should work well under certain conditions. But empirical validation, using sample splitting, holding out a separate test set, is always the ultimate judge of how well your specific model performs in the real world. Always check the out-of-sample performance.
Sound advice. Okay, let's take a bit of a helicopter tour now, beyond Lasso and post-Lasso. There are other penalized methods designed for potentially different scenarios. The source talks about different underlying coefficient structures.
Yeah.
What exactly are those beyond the sparse structure that Lasso seems best suited for?
Yeah, so beyond sparse, where only a few coefficients are large and the rest are zero or tiny, Lasso's sweet spot, we often encounter two other common structures or perhaps patterns in real-world data coefficients.
Okay.
One is called dense. This is a situation where the vast majority, maybe even all of the coefficients are non-zero. They might all be relatively small, but they all contribute something meaningful. There aren't just a few big players, it's more of a collective effort.
So lots of small effects adding up.
Exactly. And then there's a hybrid case called sparse+dense. Here you have a mix. Maybe a few coefficients are quite large and important, like in the sparse case, but you also have many, many other coefficients that are small, but definitely not zero. They're not negligible noise. They represent a sort of dense background of weaker effects.
Interesting. A few stars and a large supporting cast. Okay, so if Lasso shines in sparse settings, what method might we turn to if we suspect we have one of these dense models where pretty much everything contributes a bit?
For dense models, the classic alternative is ridge regression. The idea is quite similar to Lasso in that it also adds a penalty to the least squares objective function to control complexity.
But the penalty is different.
Yes, the penalty is different. Ridge penalizes the sum of the squared values of the coefficients. This is often called an L2 penalty, as opposed to Lasso's L1 penalty, sum of absolute values.
L2 versus L1. Okay. What are the key differences in how ridge behaves compared to Lasso because of that different penalty?
There are two main differences. First, unlike Lasso, ridge regression does not set coefficients exactly to zero. Because the squared penalty doesn't have that sharp kink at zero, there's no incentive to eliminate variables entirely. It just shrinks all coefficients towards zero, but they all remain in the model. So ridge does not perform variable selection.
Okay, no variable selection. What's the other difference?
The other difference lies in how it shrinks coefficients of different sizes.
Yeah.
Because it squares the coefficients in the penalty, ridge penalizes large coefficients much more aggressively than Lasso does, but it penalizes small coefficients much less aggressively. Think about it. If a coefficient is 10, Lasso penalizes it by 10 lambda, ridge by 100 lambda. But if a coefficient is 0.1, Lasso penalizes it by 0.1 lambda, while ridge only penalizes it by 0.01 lambda.
Ah, interesting. So it really clamps down hard on the big ones, but is more forgiving of the small ones? Well, when does ridge truly shine then? What kind of situations is it best for?
Ridge is particularly well suited for prediction precisely in those dense models we talked about, where most coefficients are small but generally non-zero. And crucially, it also tends to perform exceptionally well when your predictor variables are highly correlated with each other, what the authors call a poorly behaved or ill-conditioned design matrix.
Why is it better with correlated predictors?
In essence, when predictors are highly correlated, OLS estimates become very unstable, and Lasso might arbitrarily pick one variable from a correlated group. Ridge, by shrinking all coefficients simultaneously, tends to handle these correlations more gracefully, often by distributing the effect across the correlated predictors more stably.
Okay, so it's good for dense models and correlated data.
Yes. In those dense cases, ridge can often easily outperform Lasso because it embraces that collective contribution instead of trying to force sparsity. It's also closely related mathematically to principal components regression, though it implicitly weights all principal components rather than selecting a subset.
Okay, so we have Lasso for sparse, Ridge for dense. What if your data is maybe a mix of the two, that sparse plus dense structure? Or what if you're simply not sure which structure you're dealing with upfront?
That's where another method called ElasticNet comes in. It's designed to be a flexible hybrid. It very cleverly combines both Lasso's L1 penalty and Ridge's L2 penalty into a single objective function.
Both at the same time. How does that work?
Yeah, it has two separate penalty parameters, one controlling the strength of the L1 Lasso part and one controlling the strength of the L2 Ridge part. Typically, you'd choose both of these parameters using cross-validation.
So it's designed to kind of give you the best of both worlds, letting the data decide how much L1 versus L2 penalty is needed.
In essence, yes, that's the goal. This combination gives it much greater flexibility. With proper tuning of those two penalty parameters, ElasticNet can often perform well whether the true underlying regression coefficients are approximately sparse or dense or somewhere in between.
Does it still do variable selection like Lasso?
Yes. Importantly, it generally retains the variable selection property, which it inherits from the Lasso L1 component of its penalty. Unless you specifically turn the L1 penalty component completely off, making it just Ridge, it can still set coefficients exactly to 0.
Very flexible. Okay, and then there's one more mention. Lava. That sounds volcanic, perhaps more specialized. What's Lava specifically designed for?
Yeah, the name is evocative. Lava is designed specifically for those sparse plus dense settings. We discussed that scenario with a few big coefficients and a lot of small, non-zero ones.
The stars in the supporting cast scenario.
Exactly. Its approach is quite clever and different from ElasticNet. It tries to estimate the coefficients by explicitly splitting the parameter vector into two parts. A dense part, which gets penalized using a Ridge-like L2 penalty, and a sparse part, which gets penalized using a Lasso-like L1 penalty.
And how does it know which coefficient goes where?
That's the neat part. The minimization program itself automatically determines the optimal split for the given data. It figures out which coefficients are best treated as part of the sparse component and which belong in the dense component to minimize the overall objective function.
That sounds quite sophisticated. Does Lava also perform variable selection, setting coefficients to 0 like Lasso or ElasticNet?
No, interestingly, unlike ElasticNet, unless its L1 part is 0, Lava does not perform variable selection in the sense of setting coefficients exactly to 0. Its penalty structure is unique. It ends up penalizing large coefficients, more like Lasso would, less aggressively than Ridge, and small coefficients more like Ridge would, less aggressively than Lasso.
So it handles big and small coefficients differently.
Exactly, and the authors highlight that in true sparse plus dense models, Lava can, both theoretically and in practice, sometimes outperform Lasso, Ridge, and even ElasticNet. And with appropriate tuning, it can also adapt and match their performance in purely sparse or purely dense settings too, making it potentially a very versatile option if you suspect that mixed structure might be present.
Wow, okay. The source includes a simulation example, Table 3.1, that really seems to illustrate these relative strengths quite beautifully, doesn't it?
It's a fantastic little example, yeah. They ran a simulation with, I think, N100 observations and P400 variables, so definitely high dimensional. They tested scenarios designed to be sparse, dense, and sparse plus dense.
And what did they find?
The results were very clear and lined up perfectly with what we just discussed. In the sparse setting, Lasso and Lava performed best. Ridge did poorly, as expected.
Okay.
In the dense setting, Ridge and Lava performed best. Lasso struggled because it was trying to impose sparsity where there wasn't any. But crucially, in the sparse plus dense setting, Lava was the clear winner, performing better than both Lasso and Ridge, and presumably ElasticNet too, though they might not have included it in that specific table.
So it really shows the importance of picking the right tool for the job, or at least a tool like Lava or ElasticNet that can adapt.
Exactly. It vividly demonstrates that the underlying structure of your coefficients really matters, and choosing a method well suited to that structure, or one flexible enough to handle different structures, can make a big difference in your prediction accuracy.
So this all sounds incredibly powerful. We have this toolkit now, Lasso, post-Lasso, Ridge, ElasticNet, Lava. But how do you actually choose the best one for your specific data in practice? There's so many options. How do you possibly decide which one is going to work best?
Yeah, that seems like the big practical question, right? But the answer, thankfully, is surprisingly straightforward and doesn't rely on guessing the underlying structure perfectly. It's very data-driven.
Okay, how does it work?
You use that technique we mentioned earlier, data splitting. You take your available data and you split it, usually randomly, into at least 2 sets, a training set.
Which you use to build the models.
Exactly. That's where you estimate all your different models, your Lasso, your Ridge, your ElasticNet, your Lava, and you also use it to tune their respective parameters, like lambda for Lasso and Ridge, or the 2 parameters for ElasticNet, probably using cross-validation within the training set.
Okay, so you train and tune everything on the training set. Then what?
Then you take those final tuned models and you evaluate their performance on the completely separate test set, the data that was held out and never used during the training or tuning process.
And you just pick the winner?
You just pick the winner. No complex rules of thumb based on theory are strictly needed for the final choice. You simply choose the method, whether it's Lasso, Ridge, Lava, or maybe even just plain OLS on a simpler model that performs best on that test set according to whatever prediction metric you care most about, like mean squared error or R squared.
And that's a rigorous approach.
Yes, it is. The authors emphasize that rigorous theoretical guarantees actually support this very practical approach. Letting the out-of-sample test set performance be the ultimate arbiter is a statistically sound way to select your best predictive model. It lets the data tell you what works best for generalizing to new observations.
That's really empowering. Let the data decide. Okay, let's look at a real-world example they provide in the chapter. Predicting wages using data from the Current Population Survey, CPS, from 2015. They tried out different model specifications to see how these methods actually stacked up in a real application.
Right. It's a good illustration. They started with what they called a basic model. This just used the raw predictor variables available in the CPS data, things like sex, years of experience, education level, occupation and industry codes, and region of the country. Pretty standard stuff.
Okay, a simple linear model.
Then they built a flexible model. Here, they started adding transformations to allow for more complex relationships. They included polynomial terms for experience, like experience squared, experience cubed, and also added all possible two-way interactions between the basic predictors.
Getting much more complex now.
Definitely. And then they went even further with an extra flexible model. This one included sex and all possible two-way interactions between those experience polynomials and all the other raw predictors. So a really, really high-dimensional specification with potentially thousands of constructed regressors.
Wow, okay, so they have these 3 levels of model complexity. What happened when they ran standard OLS versus these various penalized methods on those different specifications? What were the results? What stood out when they looked at the test set performance, say, the R squared?
Well, looking at the results in Table 3.2, first off, OLS actually performed reasonably well with just the basic model. As expected, it probably started to overfit with the more complex models. For the flexible and extra flexible models, they applied the penalized methods Lasso, post-Lasso, Ridge, ElasticNet, Lava, and they tuned the parameters either using cross-validation or those theory-based plug-in methods.
And the winner was?
Here's maybe the most interesting or perhaps surprising takeaway for you listening. While technically Lava, using the extra flexible specification, produced the marginally best performance on the test data, achieving an R squared of 0.290.
Okay, so Lava won, barely.
Barely, because traditional OLS using just the basic set of controls was remarkably competitive, achieving an R squared of 0.288.
Wow. Only 0.02 of a point difference in R squared between the most complex model with the fancy Lava method and just plain old OLS with basic predictors.
Exactly. In this particular application for predicting log ranges, adding all that extra complexity and using the sophisticated penalized methods didn't actually buy them very much extra predictive power compared to a simple, well-chosen baseline model.
That's a fantastic insight. It's a great reminder, isn't it, that sometimes, especially maybe in social science settings where relationships might be noisy or sample sizes aren't astronomical, the classic tools, when applied thoughtfully to a sensible set of core predictors, can still punch way above their weight. What does that tell us about choosing our tools in practice?
It's a really crucial point. It tells us that while these advanced penalized methods are incredibly powerful and absolutely essential when you're dealing with truly high-dimensional data, like genomics or maybe very complex image analysis, or when you strongly suspect important non-linearities or interactions.
They aren't always magic bullets.
They aren't always magic bullets, exactly. You shouldn't just throw them at every problem without thinking. In situations where the number of relevant predictors might actually be relatively small compared to the sample size, or where the underlying relationships are reasonably linear, a simpler model like OLS might perform almost as well, or sometimes even slightly better if the penalized methods shrink things a tiny bit too much.
So consider the simple baseline. but have the advanced tools ready for when the complexity really warrants it.
Precisely. While simple models can sometimes be surprisingly effective, you should definitely consider using penalized methods when you have a large number of potential controls, or when you want to explore potentially important nonlinear relationships or interactions without risking massive overfitting. They give you the power to explore that complexity safely.
And it's not even necessarily about picking just one best method for any given problem in the end, is it? There's another approach.
No, absolutely not. That's a great point. Instead of solely relying on picking just one winner, whether it's Lasso or Ridge or Lava, you could also explore using ensemble methods.
Ensembles, combining models.
Exactly. These methods essentially combine the predictions from multiple different models. You might, for instance, average the predictions from a Lasso model, a Ridge model, and maybe even a simple OLS model. The idea is that by combining diverse approaches, you might get a final prediction that's more robust and potentially even more accurate than any single method on its own. It's like building a committee of experts rather than relying on just one star player.
Leveraging the strengths of each. That makes a lot of sense. Okay, so to recap our deep dive today, we've seen how high-dimensional data having more potential predictors than observations, or just having a huge number of predictors, poses really significant challenges for traditional regression methods like OLS. The main villain here is overfitting.
Right, the risk of just memorizing the noise in your training data. And we've explored how this powerful toolkit of penalized regression methods, Lasso, Ridge, ElasticNet, and Lava provide really elegant and effective solutions to this problem.
They do this by carefully balancing model fit, how well the model explains the data, with model complexity, trying to keep things simple.
Exactly. Often through that critical process of variable selection like Lasso does by shrinking unimportant coefficients exactly to zero, or through just general coefficient shrinkage towards zero like Ridge does for all coefficients.
And we've also seen how their unique strengths are often suited for different underlying data structures or coefficient patterns, whether the true relationships seem to be sparse, few big effects, dense, many small effects, or maybe a blend of both. This gives us an incredibly versatile set of tools for tackling almost any modern prediction problem you might encounter with complex data.
It truly is a versatile and essential toolkit nowadays, providing a practical roadmap for navigating the complexities of large data sets and building better predictive models.
Absolutely. So to leave you with a final thought to ponder, there's a profound idea from Antoine de Saint-Exupéry, the author of The Little Prince. He once said, "It seems perfection is attained not when there is no longer anything to add, but when there is no longer anything to take away."
That's a great quote in this context.
Isn't it? So if penalized regression methods, especially Lasso, kind of achieve their success by literally taking away irrelevant variables, and even methods like Ridge implicitly simplify models by shrinking coefficients, what does this tell us about the fundamental nature of understanding complex systems more broadly? Is finding the truth often about subtraction rather than addition? And how much taking away can we truly afford in our models before we risk losing critical insights or nuances? Where do you think we draw that line between achieving elegant parsimony and maintaining sufficient predictive power? What stands out to you from this concept of finding the simplest, most effective model?